So good morning, everyone. And I'm really sorry for not being there in person. I really wish that I was there today. And I hope to have the opportunity to meet you at another conference or in Cambridge again. So I'm Mihaela van der Schaar, and I have a chair in Cambridge that spans machine learning, AI, and medicine. And today my talk will be related to that. But before telling you that, let me just say a few other words about Cambridge and the Cambridge ecosystem, because you may return in the future to visit us. So we have established a few years back, as a matter of fact, 1.5 years ago, the Cambridge Center for AI in Medicine, which is a center that I'm directing in Cambridge, and that is very interesting because it has machine learning researchers like me and Jose Miguel and Pietro Leo, but also clinicians, biostatisticians, economists. So it's a very vibrant interdisciplinary research environment. And I'm also a faculty fellow at the Alan Turing Institute in London. So if you have questions about any of those at the end of the presentation today, I'd be delighted to answer any questions about that as well. Prior to this, I was a professor at a chair in Oxford in quantitative finance. So you can see that machine learning can evolve at many applications. My true passion is medicine. However, the techniques that I'm going to describe today transcend medicine and really are useful for many other applications. Finally, before that, I was at UCLA in the United States. So my research background really has changed over time, and machine learning is something I do for many years. But this type of machine learning applied to healthcare, I really have started around 7 years ago. And it's a very exciting area for me. And I really hope that it will be an exciting area for you. And today you will hear not only about machine learning interpretability, but somewhat also of a personal view about the role that machine learning can play in improving healthcare. Before I start, I'd like to introduce you to my team members in our lab, as well as to 2 research engineers that are part of both the lab and some of the center, as well as a former student. You will see here highlighted a few former students as well, but one that I would like to highlight in particular is Ahmed Allah, who is who is a former PhD student in my lab at UCLA, who is going to join as a professor at University of Berkeley next month. And the work that I'm going to highlight here comes a lot from my PhD students, Jonathan Crabb, Xiaoxi Qian, and Christophe, and also the work of Ahmed. I often like to start giving these talks by providing this quote from Sir William Osler, which is also the father of modern medicine. If it were not for the great variability between individuals, medicine might as well be a science, not an art. And what I believe that machine learning can do is turn this art into a science by developing machine learning methods. But why is medicine really so complex, and why medicine has very much remained an art over the various centuries? This is because patients and individuals are very different. They have different genetic background, environmental exposures, lifestyles, histories, and they respond differently to interventions. And this leads to different risks evolving over time, variation in symptoms, different health and disease trajectories, as well as response to treatment. So the art of medicine has been to use judgments on the basis of this diverse and heterogeneous information to manage patients effectively. And what I believe that machine learning can do is turn this art of medicine into a science. And I hope that I'm going to get many of you excited about this area. And the reason I think this area is very exciting is not only because of the impact we can make on human lives and the societal impact, but also, as you are going to see, medicine obliges us to model a diverse set of problems that are useful not only in medicine, but many other areas. Yet we would not think about these complex problems if we just think in vacuum. And we just think about problems such as classifying cats and dogs or more conventional natural language processing problems. You'll see that this complexity of medicine is very informative to model the world more generally and unravel very interesting machine learning methods to solve these problems. In terms of medicine, the reason that I'm so excited about machine learning and the role it can play is because I believe it can deliver precision medicine at the patient level, understand the basis and trajectories of health and disease, empower healthcare professionals as well as patients, inform and improve clinical pathways, enable utilization of resources that's more effective, transform population health and public health policies, which was very important as we have seen in COVID, as well as enable new discoveries, both clinical as well as new therapeutics. What machine learning can do to address these different opportunities and provide solutions for these opportunities is highlighted here. And I'm showing you here somewhat of a personal view based on some of my own research, but our lab is by no means the only lab working in this area. And the problems and solutions that I'm highlighting here are by no means the only ones. Yet I'd like to do that first before I enter in the context of what I'd like to describe today, which is machine learning interpretability. So in order to do anything in machine learning, but also in machine learning for healthcare, we need to have data. And here there are two challenges in medicine. First is that the data can often not be easily exchanged with us, the machine learning researchers, because it's private and contains information about the healthcare of the patient. So one particular machine learning tool that's very powerful in this context to enable us to share this private data is to generate synthetic data. So using generative models in order to create synthetic data that can be shared without privacy risks with researchers, as well as enable many other things such as augmentation, dealing with bias, etc., represents an important frontier in synthetic data that can be generated using machine learning. And if you want to learn more about that, I gave a tutorial together with Mihaela, my former student, last year at ICML 2021, so you can watch that. And if you are already interested in this area, we have a workshop at ICML 2022 on synthetic data that you can participate in. Another area that's emerging and that I think is very important in this, on this topic is data-centric machine learning. We know that the quality of the predictions, and if it is to talk about more complex settings such as causal inference, it's extremely important to have high quality data. And here I'm talking about noise, missing data, error in data, biases in data. And this agenda of data-centric machine learning is, I think, a very important one. And my own lab is doing a lot of research in this area, but I think a lot more needs to be done to really have a good understanding of the role of data as well as improve data when generating analytics of all sorts. About analytics, here is an area where we are moving into somewhat more mature research. And this ranges from generating analytics using automated machine learning frameworks. And again, the focus here is not to replace the clinician or the human, but rather to replace the machine learner, such that we as machine learning community, we don't need to deal with generating yet again and yet again another analytic for a task that's very simple, like for instance, risk prediction, but also many other scenarios. So automated machine learning is still a very important area, and it's important because we have many data sets with many requirements. Some of them may change over time. So AutoML is really a very important topic in machine learning, but also in machine learning for healthcare. Again, a little bit of advertisement. After ICML 2022, we have organized together with Frank Hutter the first symposium conference on automated machine learning. And this is going to take place in Baltimore just immediately after ICML 2022. So if you are interested to hear more about AutoML at its cutting edge, we invite you to that workshop and that conference. But there are many other important things in building analytics in medicine, such as estimating treatment effects, causal deep learning, time series forecasting, dealing with meta-learning and transfer learning, and many others. And our own lab, but also many other labs, are working in this area. In our case, we do a lot of work, especially on estimating individualized treatment effects and causal deep learning, as well as time series forecasting, because this represent important problems in medicine as well. Today, I'm going to talk about interpretability and making discoveries on the basis of data. And in order to create trustworthy analytics that clinicians and patients can use, we need to have not only interpretability and discovery, but also uncertainty quantification. And of course, Jose Miguel is doing a lot of important work in that area that is very pertinent here. Finally, I'm not going to talk about today, but another area that we are building in our lab is new machine learning methods that enable us to create a new human-machine partnership. And the focus here is augmenting human skill using machine learning. I'm not talking here about human-computer interfaces. I'm talking here about some new strengths of inverse reinforcement learning and imitation learning, some new types of machine learning methods that really are capable to look at how humans act, and on the basis of this, understand human decisions and provide the right information to humans making decisions over time to better empower them and collaborate with them. If you are interested to hear some of this work, one particular example besides our own website is one of the papers that we have at ICML 2022 by my student Alihan Huyuk. Is called Inverse Contextual Bandits, and the focus of that work is exactly on this human-machine partnership. But today, I'm going to talk about how we can make machine learning more interpretable and how can we come up with discoveries on the basis of machine learning. And as I mentioned, this is important in medicine, but it's also important in many other areas. Most of you are already very familiar with this and with the whole agenda of explainable AI. I'm just going to be very fast about that research agenda, and then I'm going to talk about some cutting-edge research in that area. So often we may have a black box machine learning model, maybe, for instance, a deep learning model, it may be some type of XGBoost as well. So it doesn't need to be necessarily a deep learning model, but our main focus will be on deep learning models. And the focus will be to understand how the predictions that are made, which may be of very high accuracy, are made. What is really the machine learning model looking at when making this type of predictions? And the focus here will be quite a lot in the beginning part of the talk on post hoc interpretability. When I move to discovery, I'm going to take a slightly different view. But in the beginning, I'm going to take the black box model and try to add a module on top of this black box. So I'm not going to interact in any way with the black box model. I'm going to let it be completely be trained by itself. And then in a post hoc fashion, I'm going to try to understand what has the machine learning model looked at when issuing a particular prediction. So I'm not going to interfere and create black box models that are interfered with, but rather explained immediately after. Several core references are on these slides. I'm going to refer to a few of them briefly, but there are many others. Here are just some of the few examples in terms of reviews on explainable AI, as well as a few papers which I find especially interesting, and I'm going to just very briefly highlight in the next slides to remind you about them. And then I'm going to talk about can we do better and how can we go to the next level. But before I do that, let me remind you why this is so crucial in medicine, but also many other areas. We want to increase the scientific content of these models. and we want to distill knowledge from these models. And as a matter of fact, a big chunk of the second part of my talk will deal with, can we come up with discoveries from data? But it's not only that. We want also to be able to debug model, understand model biases, and understand how these models are eventually issuing predictions and design better models. We also want to keep the human in the loop. And this is especially important in high-stake decisions. And we want to make sure that the humans understand these predictions and they can engage with them. So often, when I started this research agenda around 7 years ago, I wondered whether we, the machine learning researchers, know exactly what is interpretability and explainability, and whether we really know what would make a model explainable and interpretable. And with a master student, Owen Lahav, who was my master student in Oxford around 5 years ago, we'll put actually a large number of machine learners in front of a screen and a large number of clinicians and ask them, what do they want in terms of explanations? And what we discover is that we, the machine learning community, have really not a very good idea about what really the users of these black box models, such as in my case, the clinicians, want from an explanation. So what I've learned on the basis of that exercise, and we published that research not only in the form of Owen's thesis, but also as a paper in a NeurIPS workshop quite a few years ago. What I've done after summarizing that work was to realize that I really need to engage with clinicians in conversations to understand what they want and what they need, not only in terms of analytics, but also in terms of explainability. So as part of that, I've started an engagement session 2 years ago, which we call Revolutionizing Healthcare. This engagement session has by now more than 500 clinicians from all over the world engaged in our sessions. And you can see, if you are not having MD degree, you cannot join these sessions online live, because these sessions are really dedicated to conversations with clinicians, but you can watch all of them on YouTube. And you can see, for instance, quite a lot of conversations we had in these last 2 years about interpretability. And this is one particular setting. Another setting is just before the pandemic has started, I gave a Turing talk at the Royal College of Clinicians. And what's interesting about this talk is less what I'm saying in this talk, but more the discussion that is at the end of this talk, where I have a long discussion that's on YouTube with clinicians that are in the audience about what they would like to see with respect to interpretability of black box machine learning models. And I've made a summary of that online, and you can read about it if you don't want to watch the video. So what do the clinicians want? 3 things. 1, explanatory patient features, and that is not surprising. But as you are going to see in a little bit, we need to go beyond what current feature explainability provides us. Then something kind of logical if you think about how medicine is practiced, and that's personalized explanations using specific patients already known to each clinician. So in other words, a clinician may have a certain body of experience, may have seen a certain set of patients, and they want to interrogate the predictions made by the black box model on the basis of the experience they have and concrete examples they have seen in the past. And they want that the explanations come on the basis of this personalized experience they have. And finally, they want really to discover something new, especially the clinicians that are clinician scientists. They want to understand whether they can unravel using machine learning the new governing equations of medicine. In the talk today, I'm going to talk about all of that. Let me start with explanatory patient features, which is, I guess, the topic most familiar to you and the topic where machine learning has made the biggest progress today. So the focus is really to understand what patient-specific feature the model has looked to and when issuing a prediction for a particular patient. And the focus here is on both global, population-wise feature importance, but also individualized feature importance. So for instance, I have here a particular patient. This is an example from clinical decision support system that we have built with the cancer registry in the UK 4 years ago. And what you see here is a patient, a diagnosis of breast cancer, and what you see here is the mortality risk of this particular patient. The prediction actually of this model was validated more than 1 million patients, and you can read more about this if you are interested in a Nature Machine Intelligence we have written last year. But what's interesting with respect to this topic is, well, fine, we have fantastic predictions in terms of accuracy, but what has the machine learning model looked at? And what you see on the right side is that the model has looked at a specific set of features when issuing these predictions. And what you see here is the weight, if you like, of importance of the different predictions for this particular patient. So how can we really create such explanatory patient features? To understand this, I'm going to give the familiar example that you have seen before, partially because a lot of the early work has looked at images, but this doesn't need to be only used for images. This could also be used for patients and patient features. And the two models that I'd like to highlight here are integrated gradient and Schaar. And what's important here is to highlight what part of the input X motivates this particular prediction. For instance, a model might pay attention to certain parts of the image to detect a dog, or in the case of the patient prediction of mortality, a certain set of features of the patient to predict the mortality risk. How does this really work? Let's briefly, quickly review this. I know this may be familiar to most of you, but I just want to remind you because later I'm going to contrast with this. We start an input. Here is an image that we fit to a black box model. For instance, this can be a deep neural network. And the black box learns to predict if this is a cat or a dog in the picture. How we want to interpret the black box prediction, to do that, we need to select a scalar output from the black box. The typical approach is to use the ground truth label to select this suitable probability, as you're seeing here. Then we can simply use a feature importance method to measure how each feature contributes to this probability. We can then, obtain a saliency map that is able to measure how each feature contributes to this probability. And the saliency map will highlight the most relevant parts of the image according to the model. We are highlighting here a particular example. And this is the kind of the basic idea beyond most feature important methods such as integrated gradients. Now, most of these methods allow us to do feature importance at the global level, but what's even more interesting in medicine is if we can do that at the individualized level, meaning we can identify which features are important for a particular individual as opposed to another. In that regard, in medicine, we need to go one step further, and we need to identify not only what features are important for John as opposed to Bob, but also the number of features that are relevant for each instance. So we cannot always have 5 features or 3 features. We need to learn that maybe for Bob there are 5 features and for John only 3 features. And this was actually not possible easily before. So this is why a few years back we created this model called InVase. I'm not going to highlight it too much here, but the only reason I want to say briefly that this is a powerful method is because of 2 reasons. So first, again, if we want to make predictions or risk, it enables us to make predictions, but also to learn the number of features that are important, and is doing so using a reinforcement learning method. And the reason I'd like to highlight that is because most of you may think about reinforcement learning mainly in the context of choosing actions in an online environment and maybe as in a form of a decision support system. But reinforcement learning is also useful in settings such as feature interpretability, for instance. And we use reinforcement learning in this Invase method to select what features are important for the prediction of the model. And the way we use reinforcement learning is to make observations about the patient and then select actions on the basis of these few observations. And these observations could be very cheap observations about the patient. And then we can determine rewards for these observations, which in this case are actions, and potentially acquire additional features, thereby either viewing this as a post hoc interpretability or used as engine at the beginning of the model to acquire additional information about the patient, turning it thereby into an active sensing framework. Ultimately, we learn a policy which selects the best actions given the features of the patient. So a very simple actor-critic framework which is used for feature importance to explain black box models. And again, I'm highlighting this because I think that this type of simple machine learning, reinforcement learning framework can be used to do feature importance in many other scenarios as well. However, in medicine, we need to go beyond such simple static predictions. In particular, we need to do time series forecasting. We need to explain the predictions of time series forecasting models. We need to be able to do heterogeneous effect estimation and explain why a particular model issued these particular predictions. And finally, we need to do a lot of clustering and phenotyping, as well as other unsupervised learning models, and also interpret the findings of such models. And these are three areas for which much less research or no research has been done today. To illustrate why this is challenging, let me take the example that I just showed before. I highlighted you this example where we used Invase to see predictions of the risk of the patient. But what you can see here, if you look at this picture of feature importance, you see that these predictions are changing at times over the years. So you see that at year 2, at year 3, the features that are important are very different than at feature 1. And as a matter of fact, there is a very nice paper in NeurIPS 2020 by Mihaela and co-authors, where they have shown in a very powerful way that standard feature important methods perform poorly for time series. And this is not only true for Invase, which is our method, this is true more generally. So you see here a toy example where we have the true saliency map of features and feature importance over time. And then you see a variety of well-known machine learning models such as Schaar, Lime, integrated gradients. And you see that actually they are not able to correctly identify what features were important over time. So they are not able to uncover the ground truth. So what makes really time series special? For that, I'm going to choose an example, not from medicine, but rather financial example, just because this is more familiar to everyone. And this graph shows a fictional security price over time. And what you can think about is that a simplistic model will recommend to sell just after a local maximum and to buy just after a local minimum and to wait otherwise. And when the recommendation to sell is to sell or to buy, 3 consecutive time steps are required as a context. Yeah. So this is what we see here. We see the importance of this context, of the time context, when we do these predictions. And what we really need is to make sure that this time context is taken into account when we create explanations. So maybe I should just say one more thing, that this time dependency is crucial really for the model. And at each time step, the model prediction provides a decision based on the previous time steps. For instance, in this case, let's assume the 2 previous time steps. And of course, this is an oversimplified example, and our machine learning models do much more, but this is just to anchor the idea. And in fact, recurrent models are inherently endowed with this notion of context because they rely on memory cell. And this might explain the poor performance of model agnostic methods to identify saliency maps features for recurrent neural networks, as identified in the paper of Mihaela. So these methods that are static and are trying to understand the predictions in a static fashion really forgot about this time context. So if it is to apply LIME, SHAP, learning to explain, deep lift, you are going to miss this time context. So, sorry. Okay, so how to detect really these saliency features in the time domain? For that, we provide a perturbation-based method. And the premise here is the salient features affect the model's prediction. And we can detect the saliency features by feature perturbation. And if the feature perturbation does affect the prediction, then we do have a salient feature. So for instance, you see that in this case, for instance, if we decide to sell, it is this context that makes you change potentially the prediction and the decision if the price, for instance, beforehand was high or low. So this represents a salient feature for the model. So in a paper that we published last year that we call Dynamask, we looked at how this time context enables us to understand better and interpret predictions made by black box models in the time series setting. So typically these saliency methods are treating each input as a feature, and the time dependency, as I mentioned, is ignored. Yet, by introducing these dynamic perturbation operators, we are able to perturb each feature at a particular moment in time by using neighboring times. So what you see here is the perturbed input and how it looks like as a function of a window of past contexts. This is a linear combination of past contexts, and the time dependency is integrated in this perturbation. So for instance, this provides us this type of window perturbation where we are trying to explain the prediction at the current time on the basis of context across time. And most of the time, of course, we would like to be causal. So we are going to use a window that precedes the current time point. So we are going to use previous time points rather than future time points to explain this prediction. Now, how this Dynamask framework that we have introduced works? So we have the time series input prediction that was actually on the basis of which we use a black box model to issue predictions. And we now try to really understand what has the black box model looked at when issuing this type of predictions. So we want to learn this mask, this dynamic mask over time of feature and feature importance. Green is important, red is not important. So we are learning that by introducing this perturbation operator, and we are perturbing in this way the features that are exposed to the black box model and create a perturbed output. The error between the original output and the perturbed output is information that we are going to use to enable us to create and develop this mask. What's important when doing that is to make sure that these masks that we are creating are parsimonious. In other words, it would be useful if everything is important. We really need to learn the minimum number of features that are important for a particular prediction. And the way to enforce parsimony is, for instance, by enabling the user to select a fraction of the most important features on the basis of which they would like an explanation. Or alternatively, you can learn what is the minimum number of features that will really not reduce the prediction of the output. So what we are going to do in Dynamask is going to add a regularization to enforce sparsity of this feature importance over time. So this is an important thing. Another important part is what happens if we want to avoid quick time variations of the saliency map. This can be a prior belief or a preference of the user. So what we would like to do then, we would like to introduce another regularization when learning this dynamic mask over time that is penalizing the saliency jumps over time. And you see here an example where by introducing such a penalty, we are reducing the number of features that are important and whether they stay important over time. Now, how well does Dynamask do? You see here, again, the example I showed before. This is a synthetic example, but we have in the paper a few other examples with real data. But it's simplest to understand this using this toy example, where you have the true saliency map on the left upper corner, and then you see on the right upper corner Dynamask, and you can see actually that Dynamask is identifying correctly most of the time the feature and feature importance over time, and significantly better than existing methods that are used for static interpretability. By no means Dynamask is a perfect method. We introduced this, as I mentioned, last year's ICML, but a lot more progress needs to happen on time series interpretability, and methods for post hoc feature importance over time need to be developed to really understand what are black box prediction models, whether it's recurrent neural networks or other machine learning models. What features are they looking at? What features are they looking over time? So I hope I entice at least a few of you to look at this agenda, which is, I would say, a very unexplored agenda. Let me now move to another area that is, in my opinion, unexplored and very important in medicine, but also in many other areas. Explaining unsupervised models. So most of the research that we see on machine learning interpretability and explainability focuses on supervised models. But the reality is that we often need to explain unsupervised models. So we need what we call label-free explainability. So we will try to interpret the prediction of a model that was obtained through unsupervised learning, for instance, like in a clustering model. In the most standard setting, we have an encoder that provides a representation of the data, as shown in here. And here, both the neurons are scalar functions of the input. And of course, I can backpropagate both of them to obtain saliency maps. But how do I know which features are the most important for the encoder to assign this representation? Unlike in the previous case I showed to you before, I do not have access to a label. So there is no obvious way, unlike in the past, to choose between these saliency maps. When it comes to example importance, the absence of the label is also problematic. I'm going to talk more about example importance later, but I want to say that this is true for both feature importance as well as example importance. And both of these considerations motivate the need to develop something new to explain unsupervised model predictions without the presence of a label. So this is why we call this a label-free explainability. And this is a recent paper which Jonathan will present next week at ICML 2022. And again, the big challenges we are going to try to identify is really, given the fact that we don't have labels, how do we compute a loss? And how we do this label-free explainability. So let me focus on this label-free feature importance first and ask how to combine these two saliency maps. We start by noting that functions F1 and F2 typically correspond to neuron activations, and therefore we propose to weight saliency map according to the corresponding neuron activation. You can convince yourself that this also makes sense for linear combinations of neurons. In this paper, we show that this definition that I'm showing to you here guarantees a completeness property, which is very important for feature importance methods. So we show that analytically. And we also show that this expression is invariant with respect to orthogonal transformations of the representation space. Hence, the two representation spaces with the same geometry will lead to the same feature importance. So this works for linear combinations of neurons. We prove the completeness property, and we show that it's invariant to the latent space symmetries in the paper. And again, the theoretical analysis can be found there. Can we take this now to example importance? Well, the challenge here was to compute a loss without a label. And often encoders are not trained by themselves. You will typically have a decoder that will reconstruct the original input, and this reconstructed input can be compared to the original input through a loss. Again, we can compute the gradient of this loss with respect to the encoder's parameters. And we note that the gradient is only with respect to the encoder's parameters. And this is because our focus is to explain the representations learned by the encoder in a label-free explanation. By doing this for all the training example, we can dig up examples that have similar gradients and thereby provide label-free example importance. So this is the example found here, and this is how we are identifying these label-free examples. This is just a very brief introduction to this setting. In the paper, we have other more complex experiments, and we show importantly that these label-free methods work in a variety of settings. You can notice that I didn't specify a specific type of example importance or feature importance. As a matter of fact, this method can be used on top of any such method, and it can work together with any such method. So this label-free explainability can be viewed almost as a wrapper that can be put around any existing feature or importance-based method. On top of that, we demonstrate that the resulting interpretation methods give sensible results for a variety of unsupervised models. And we go through many different types of examples. And since our framework works for this wide variety of models, we can even compare them. We can see which models are best and in what case. And we illustrate this with different types of use cases of representations learned by various encoders. But another thing I'd like to highlight, and this is unexplored, and this is why I really would like to bring this to you, to your attention. We also have at the end of the paper, we use this method to explore the interpretability of disentangled VAEs. And many people made a very big deal about disentanglement of VAEs. But what we show in this paper is that the saliency maps of these models often exhibit surprising and strange behaviors. And the disentangled units pay attention to features that at times may make sense, at times may not make sense. So what I find interesting in this context and unexplored is how can we use label-free explainability methods, such as the one I highlighted here, to better understand what these different classes of autoencoders and more generally other generative models really learn, and can we use these explanations to better inform the way in which we design autoencoders. An important frontier, not only for interpretability, hence, and unsupervised interpretability methods and understanding what unsupervised interpretability methods look at, but also use this information to build better, maybe unsupervised learning methods. Now, can this all be improved? Well, previous methods don't explain why some features or examples are important, and they only take the model's output into account and don't clearly indicate when we should be skeptical about the model. Also, as the clinicians that we discuss these methods with have said, the type of explanations we provide are not always useful to them. They would like to have explainability in terms of their own knowledge, their own experience. And the explainability we give doesn't always refer to what do they already know and the cases and the patients that they have seen in the past. So this is why we decided to design another type of explainability that goes beyond explanatory patient features and rather provides personalized explanations, so personalized to the user, to the clinician in our case, that uses specific instances, in this case, specific patients, that are already known to each clinician, and explains the predictions made by a black box in terms of these explanations. Before I show to you how we do that, let me explain to you why, remind you and explain to you why current methods that provide explainability through examples are not sufficient. Why example-based explanations are not sufficient. These explanations typically contextualize the prediction by presenting similar examples. For instance, in this case, similar dogs. Yeah, in the case of image explanations. And of course, we have very powerful methods to do example-based explanations that I personally like very much, like influence functions, or for instance, the representer theorem. And these, of course, are very powerful, but this is often not enough. And the way in which these methods usually work, they build this type of example-based explanations, for instance, in the case of influence functions, by using the probabilities of prediction, in this case, both probabilities together, to compute a loss function, such as, for instance, cross entropy, and then compute the gradient of this loss with respect to the parameters model, and do the same for all the training example and find related examples that have similar gradients. But the trouble with this is that this is not personalized, and the examples that methods such as this find are not personalized to the user given what they know. They find examples that are influential from the pool of examples that exist in the dataset. What we would like instead to have is that if, for instance, let's go back to a more medical example. I have Nancy here, and she was just diagnosed with cancer. And we have a black box machine learning model that issues the prediction of cancer for Mary, which is quite high for the next year. We would like to understand why this prediction is made, and the clinician of Nancy, or even Nancy herself, but in this case, let's take Nancy's clinician, would like to have an explanation of this prediction in terms of a mixture of previous seen patients by Nancy's clinician. So they would like to have an explanation in terms of a corpus of historical patients seen by clinicians. And you see here, for instance, that I put an American flag near Nancy. So Nancy's clinician is an American clinician, so I would like to have an explanation in terms of a corpus of American patients. The reason I mention that is that often we have models that are developed in one country. For instance, we have developed for breast cancer a model based on the UK data set of breast cancer patients. But in our work that I mentioned to you before, we showed that this model is also useful in the United States. So we took the model across countries, and we want to see if the model is still making sense if the clinician is in a different country. And this provides a way to understand, but also explain and debug the model. So if you would like, as I mentioned before, to see a mixture of previous seen, to explain a prediction in terms of a mixture of previous seen patients by this particular clinician in the United States. So what I would like is user personalized explanations. So ideally, we would like to start with a data set of UK patients that have cancer, train a model like we have done in this adjutorium framework, and then be able to explain the predictions of these black box models to a clinician in the United States using the American corpus of examples, and to a clinician in the UK based on the United Kingdom set of examples. So we would like to issue predictions that are such mixtures of previously seen patients. And we would like to enable the user of the model, for instance, the clinician, to specify the number and the type of examples that they would like explanations in terms of. And it could be that maybe a clinician that's more experienced, for instance, may have a larger set of examples or a more accurate set of examples, while another one that's less experienced, a smaller set, and maybe a less accurate set. Yet we would like to be able to explain the predictions given these types of personalized corpus. So for that, we have developed this method that we call SimplEx, which gives the user freedom to choose the corpus of examples to explain the model predictions. And an advantage of this is that this corpus of examples does not need to be from the model's training set. It could be something that's completely different and disjoint. The black box model has been trained on a particular set of training examples, and this is no longer accessible. And we have now a user of the black box model that wants to provide its own examples and get explanations in terms of these examples. So let us start with how we do that. So our task is to take this particular example, this particular instance X, and explain the predictions made for X using the black box model F. For instance, as I mentioned, an example could be a risk prediction model where we want to predict the mortality of the patient X using a risk prediction model, and we obtain the label Y. And our task is to explain why. And we would like to do that using a corpus of examples, which are a set of individuals that we are going to use as a reference, and we call this a corpus. Of course, this example will have their own predictions, and this brings up the question, can we decompose our example X in terms of the corpus of example in order to reconstruct and explain the black box prediction Y? How can we do that? Well, let us start with a naive attempt to do that, to see why this is non-trivial. We explain X as a weighted combination of the corpus of examples, and in this way you could interpret the weight, we can interpret the weight as a measure of the importance for each corpus example. The problem with this approach is that the black box will typically be a nonlinear map. And hence the weights we have here and that we use for corpus decomposition in the input space will not necessarily be the same weights for the output space. Hence, if you aim to decompose the predictions in the output label space, you will see that the output space will have another set of weights that is typically different than that in the input space. And hence, we cannot interpret the weights in the feature input space as a measure of the weights for the black box predictions. The weights will not be having their counterpart in the output space. Things can get even worse if F is non-convex. And in this case, the decomposition of the output space may simply be impossible because the output is outside the corpus of the convex hub. So what is really happening here? And what are we really doing wrong? Both these issues really highlight the fact that the input space may not reflect necessarily the way in which the black box model F organizes these examples. Yeah. And as a matter of fact, very often we have a representation of the black box model in a latent space, which is then used to create the labels through a linear transformation. So usually black box models F consist of these two stages. First is creating a representation and then only having a linear mapping to the output space. Hence, the latent space seems to be the right space to perform this corpus decomposition. And then, because this is linear, we can easily use this corpus to explain the examples. So how can we do that? So the black box model F can be decomposed, as I mentioned, in this linear function L and this nonlinear function G that is learning the representation. We can explain the predictions F by some example X. And the corpus of examples C is used as a reference. And this corpus is provided by the user. We map everything in the latent space, H, using the function G, and we create a function G of this latent space, as shown in here. And what we create is a corpus HAL in the latent space this time. And we find the best corpus decomposition of the example in this space. Of course, it may be that we cannot perfectly find the composition, and we may have a residual, and this will lead to an error. I'm not going to discuss too much about this in this particular talk, but a lot of these details are in our paper, and we discuss the importance of coming up with this decomposition and the impact that this error has. Now that we are able to do that, we can do what I mentioned before. We can take a data set, for instance, of patients that was trained somewhere, for instance, in the United States. Then I can take a model, for instance, a multi-layer perceptron, to learn, to issue predictions. And then I'm using both an American as well as a British doctor to interpret these predictions. And the American doctor will sample an American corpus and the British doctor a British corpus. And we can use SimplEx to create predictions to help each doctor to understand the model's predictions. And the way this is created is by creating, again, these mixtures as learned in this later representation space that enables us to learn with respect to this corpus how the different weights look like. Now, the reason SimplEx is really quite useful is because it enables us to keep the humans in the loop by presenting examples chosen by the users as explanations. It also enables us to debug the model in the following sense by presenting example for which the model extrapolates and understanding errors associated with it. And finally, it enables us to go beyond current interpretability models and methods in the following way by enabling a unified example and feature-based explanation. So through SimplEx, we are able to combine these two approaches of example and feature-based explanations. And also it enables us to capture insights from the model's latent space and better understand how these different black box models learn representations in the input space. And this is something that can be capitalized on both for the sake of understanding unsupervised models, but also potentially for other purposes. Again, this is just the beginning, I would say, of a very, I think, exciting research agenda on machine learning interpretability, combining these ideas. At this stage, before I'm going to talk about quite a different way of looking at machine learning interpretability, I want to stop and ask whether there are any questions and maybe give a 5-minute break if you would like to have one.
Good. Yeah, maybe we can have a few questions and then the break. Any questions from Mihaela? Yeah.
Thanks so much for the interesting talk. I was very interested to see this series. I have one question. You mentioned for Dynamask that you introduced regularities to enforce sparsity and stability over time. Does it still reflect the model, or can it drive the model unfaithful to the actual black box?
I apologize. I do not hear completely your question. You are asking something about whether it reflects the black box. I apologize. I don't hear very well.
In Dynamask, you enforce regularize to make the prediction look more nice to the user.
Oh, very good. Dynamask. Yeah, I understand. Thank you very much. I understand that my explanation was not good and interpretable. So no, so Dynamask is a post hoc interpretability method. All the methods I highlighted here, whether it's Dynamask, whether it's the unsupervised model explanations, or SimplEx, they are all post hoc interpretability. They are not doing anything to the model. The model itself has been regularized potentially by the designer of this black box model. We are not touching the model. The regularization you see in Dynamask is with respect to the mask we are learning. So we want to make sure that the mask we are learning is both sparse. In other words, we don't learn too many features that are important, such that really the method is truly useful in pointing us to the most important features that were important over time for this prediction. But also we need to make sure that we have, if you like, that these features are contiguous over time, so they don't turn on and off. So it's with respect to the mask that we are learning that this regularization is imposed. Does that make sense? Yeah. So it's not with respect to the model, but it's with respect to the learning of the mask of the already trained black box model.
We have one more question. Hi, can you hear me?
Yes.
Okay, so you mentioned label-free explanations and you wanted to surface examples which are relevant for a particular prediction. And you also had SimplEx in there. So I was wondering, have you tried in terms of looking at these contrastive losses and seeing if contrastive losses already surface examples which are relevant to a given example?
So I'm not sure I hear very well, and I completely. Are you referring to the unsupervised example case or supervised example case?
Is that better now?
Yes, much better.
Okay, sorry. So,
no, I apologize.
Oh, no worries. I think I was moving the mic in the wrong way. So my question is related to the label-free explanations. Once you try to identify examples which might be responsible for a particular prediction, and you also had these self-supervised objectives such as SimplEx, which are contrastive in their formulation. So I was wondering if contrastive losses already capture a lot of this information, what you're interested in, by surfacing examples by computing that distance explicitly using the predictor.
So what we are able to do in here is really post hoc analyze these different models and look at what examples were, if you like, most pertinent to that particular prediction. We are not using this, you can compare, if you like, different types of methods and their ability to use additional data. For instance, through self-supervision or through other, if it's clustering, for clustering purposes, or if it is autoencoders by learning representations. So we just are able to expose, if you like, what has been learned. And hence we are able to pinpoint that maybe some methods are already inherently capable to create, if you like, more effective representations and explain them. But we are not, if you like, judging the performance of these methods. We are judging, if you like, or we are providing an insight into what have they learned and trying to explain them. So for instance, when I talk about disentanglement, the reason I was able to make a judgment is because often people claim that a certain disentanglement has been achieved. And what we are showing is that if you post hoc interpret this type of disentangled VAEs, the reality is that the explanations that come out of it are not really leading to a disentanglement of what has been learned. Do I make sense? So it's not a judgment on the performance or the importance of certain examples or the performance of certain methods, but it's more with respect to what they have learned. We are trying to expose or explain post hoc what they have learned. However, you are right that maybe this can be now used to design better self-supervised methods and inform self-supervised methods. But I think that that has not been done. And I think that this is not captured directly by current self-supervision methods.
But in the interest of time, I will have the last question for the break.
I kind of can hear you.
Okay, then I'll try and speak to you. So my question was about the final example where you're embedding in the listen space using the feature. somehow your model is learning a useful metric inside this data set. So we can compare examples that are close by. Yeah, I was just wondering why this is a useful thing to assume that the model will do. Because the last layer that we learned is a linear classifier entity. Somehow the model only needs to learn to linearly separate examples that I would say flat, as opposed to necessarily learning that examples that are close in a metric are somehow the same. Like I can still have examples that are very far apart, which are still the same type. So I was wondering if that interpretation makes sense.
I think I kind of have heard your question. I'm not 100% sure, but it was with respect to feature-based explanations. I think, and why, given this latent representation, how can we best learn this feature? We have a very nice example in the paper, in the SimplEx paper, in this NeurIPS 2021 paper, that makes this point actually very, very aptly, with both an imaging example as well as a mimic time series example. I'd say, given the complexity of discussing like this, I'd want to point you to that particular example in the paper, which talks about, I think, what you are asking.
Okay.
And has a very beautiful figure to highlight that. Maybe we can take 5 minutes of break.
I think so.